Awesome. So I want to talk to you now about the mathematics of some popular games like Sudoku, the Rubik's Cube, the game Set, and others. So I want to start with Sudoku. And Sudoku has tons of interesting mathematics. So Sudoku is the type of puzzle that's here on the left part of the screen. And let me just quickly tell you what the rules of Sudoku are. So in a Sudoku puzzle, you have some clues that you're given when you're given the puzzle. So these are these numbers that show up in here. And then you have to complete the puzzle without violating the rules that are the following. In every row, the numbers 1 through 9 shall appear. In every row. Then in every column, the same is true. In every column, the numbers 1 through 9 shall appear. In every one of the 9 columns, the 9 rows. And then in every one of the 3 by 3 subsquares, the 9 cells in these 3 by 3 subsquares, the numbers 1 through 9 have to appear again, okay? So you cannot have repetitions in each row, you cannot have repetitions in each column, and you cannot have repetitions of numbers in each 3 by 3 square. And that's it. So you need to fill out all of the entries without violating those 3 rules. Okay, so that sounds fair. So I want to consider the following question about Sudoku puzzles. And it's, what is the minimum number of clues in a valid Sudoku puzzle? And let me be more precise on what do I mean here by valid number of clues, the minimum number of clues. So a clue is one of these initial clues that you're given, the initial numbers that you're given that are already filled in when you're given the puzzle. Okay. So if you, for instance, this puzzle in here, you can count how many numbers are filled in, and that's how many clues you were given. And then a valid Sudoku puzzle, the word valid means that it's a puzzle that has a unique solution. Because for instance, imagine that I give you a 9 by 9 grid and it has just a 1 in the top left corner, so where the pointer is now, imagine that that's a 1, and nothing else is filled in. That's it. Then you can imagine that if I give this to all of you, some of you are going to come up with different answers because, well, I'm just giving you one clue. There's probably tons of ways to fill out this 9 by 9 board if I just give you that one clue. So that's not a valid Sudoku puzzle. That was just too few clues. So my question is, what is the minimum number of clues such that you can find a Sudoku puzzle that can be solved uniquely when you're given that many clues? Okay. So for instance, can I find a 9 by 9 board that has only 10 clues that can be solved uniquely? Or maybe that has 15 clues that can be solved uniquely, or 20 clues. What is that minimum number so that you're able to find a Sudoku puzzle with that many clues with a unique solution? And we actually know the answer to this question now, but it took a lot of mathematical, a lot of computing power and certainly some mathematical ideas to be able to reduce the number of computations we had to do. So the answer is 17. There are actually, not just one, there are several Sudoku puzzles with 17 clues that have a unique solution. Needless to say, they're super hard to solve, but there are. And what strategies can we use to prove that indeed 17 is the smallest? Because we have found some with 17. Now the issue is, how can we know that there isn't one with 16 clues? How can we know that for sure, if you put 16 clues in a 9 by 9 empty board, there's not going to be a unique way to solve that puzzle? How can we know that? Well, one strategy to use is what's called brute force. And mathematicians call brute force strategies that are of the form, check them all. Check all possibilities and just go through every single one of them and just check them all. So that's what brute force stands. And I see there are two different types of brute force approaches you can make here. The very first one can be, well, start with an empty 9 by 9 board, and then one thing you can do is choose 16 cells, 16 out of the 81 cells, and put numbers in them. Now there are tons of ways to do that because, well, there are tons of ways to choose 16 cells, and then for each of those you can just put numbers 1 through 9. And then check if that set of clues will lead to a unique Sudoku at the end when you solve it. This is a slightly problematic approach because it's not even clear that if you just choose any 16 cells and then you put in some numbers, it's not even clear if you can solve that. Because if you choose, for instance, 2 cells in the same row and you fill them with the same number, that's not even a valid Sudoku, so there's no way to solve that. So you'll be wasting a lot of time or computer power going through a lot of cases in which your starting clues will not even lead to a solution. So that's probably not the best approach. A second approach is, okay, fine, so let's fix that a little. Instead of just picking 16 cells and just putting whatever numbers you want in them, go and look at all possible Sudoku boards, all of them, all solved Sudoku boards. And then from those that you know that were solved, that are completely solved, choose 16 cells, 16 out of the 81 cells, and remove all of the other ones. Remove the numbers in all of the other ones. So you're only going to have those 16 to start. At least you know now that there is at least one Sudoku, one way to solve that Sudoku puzzle. Because you started with a solved Sudoku, chose 16 of the cells, remove all of the other ones. Well, you know that you can solve it in that one way. So the question is, if I do that, can I solve that in a second way? Okay, and if you can, then that said it was not a valid Sudoku puzzle. It was not a valid set of clues. And that's the approach that we're going to take. So let's take all Sudoku boards, all of the solved ones, find all of the possible 16 choices of 16 cells, and we're going to start with those 16 and check if we can solve that Sudoku uniquely. Okay. Now the issue with that is that there are 6.6 times 10 to the 21 Sudoku boards, different Sudoku boards. That's a lot. That's quite a lot. So if you actually want to do this, it's going to take 300,000 years for a computer to check every possible Sudoku grid for every possible 16 clue starting position. And if you know some combinatorics, you can actually check how many things a computer will have to check for every single Sudoku board, those 6.6 times 10 to the 21. You're going to choose 16 starting positions out of the 81. So that's 81 choose 16, if you compute that number. Then if you multiply 6.6 times 10 to the 21 times 81 choose 16, that's how many different starting positions you have to check to see if you can solve those uniquely. So that's too hard. So we're going to reduce 2 sentences. The every possible Sudoku grid, I don't want to check them all. Is there a way to reduce how many I have to check? If so, that's going to cut my computational, how much I have to compute. And then the second part that we want to reduce is checking every possible 16 cells starting position. Ideally, if you can reduce that, then you reduce how much you have to check. So how can we reduce the every possible Sudoku grid? Well, here's where a lot of terms from abstract algebra are very helpful. The first one is symmetry. A lot of Sudoku boards are symmetric. And what does that mean? Well, it means that you can apply a certain rule to one Sudoku board to get the other one. And you can do it, and you can reverse that. If you apply the inverse of that rule, you're going to get the original one. Okay. So for instance, one possible symmetry here is exchanging the set of 3 rows that are colored here. So for instance, I can put the 3 blue ones on top, the 3 yellow ones on the bottom. So from the top here, they went to the bottom, and the green ones from the bottom to the middle. Okay. So if I exchange those 3, I get a new Sudoku board, because for instance here in the top left corner I have a 2, whereas in the original one I had a 3. So these are different. But one can check that if you know how to solve the left one, then you know how to solve the right one. And the idea is, well, anything that you can do to the left one, if you then switch the bands of 3 rows in the same way that we did, you can do to the right one in here. So there's actually not much difference between these 2 boards. And you can find similar rules between similar symmetries or other type of symmetries that you can apply to a Sudoku board. For instance, you can rotate a board. So if you take this same board and rotate it 90 degrees clockwise, you get this one. Now imagine that you actually now realign the numbers again. So this top one is a 7, right? That was the number in there. So again, this is a different board from the original one because it has a 7 in the top left, whereas this one has a 3. So they're different, but anything you do to the left one, you can do to the right one and vice versa. All you're doing is really just rotating 90 degrees. So that's not going to change. If one can be solved with 20 clues to start, the next one can also be solved with 20 clues to start. It's sort of like what you can do to one, you can do to the other one. You can rotate it 180 degrees, 270. So those are some type of symmetries you can apply. You can also, so for instance, this is a similar one to what we had done. We can change the stacks of rows, the 3 ones. We can change the order between the 3 sets of 3 rows. You can also, this one is, let's see if you can figure out what we did from the original one to get this one. So the colors are the same, and if you see actually rows 4, 5, 6, 7, 8, 9 are the same. But within the yellow rows, within the 3 yellow rows, we actually exchange them, right? We exchange rows. And when we do that, we don't violate any Sudoku rule. And again, anything that you can do to the original board, you can do to this one. Okay? You can also reflect. So imagine that you take the original one, you can reflect across this red line, this red diagonal line. You're going to get a new Sudoku board when you do it. But again, whatever you do to the original one, you can do to this one after you reflect. And the results that you get for the original ones are going to be the same that you get for this one. So using this idea of symmetry, of taking all of these boards and treating them as one, we can get tons of boards. For instance, in this example, I have 6 boards in here that are the same as the original one, or at least symmetric to it. So I can start reducing how many things I have to check. Just check 1 out of them. Don't check them all. And so there are many other, given any Sudoku board, there are many other type of symmetries. And maybe you can think of a few others, right? So for instance, we did some things to rows. Can we do them to column? The answer is yes. So how many? How many can we actually get? Well, let's count. So one thing I can do, which I haven't talked about yet, is take a Sudoku board, right? Which, for instance, this one, and you can take all of the number 1s and replace them by the number 5, and all of the numbers 5s and replace them by 9, and the 9s you replace them by 2s, and the 2s you replace them by 3s, and you keep going so that you replace every number with some other number without any repetition, and you're gonna get a new Sudoku board because everywhere that you had a 1, you're now gonna have a 9, and so on and so forth. So there are 9 factorial permutations of the numbers 1 through 9. That's a fact that you're gonna learn in abstract algebra. So you can apply any one of those 9 factorial permutations to all of the numbers in a Sudoku board, and you're gonna get a new Sudoku board, or a potentially new Sudoku board. Well, in this case, for sure a new Sudoku board, unless you use the identity. So that's 9 factorial new boards that you can make out of this one. Okay? And then what I talk about, you can maybe take the 3 rows, the yellow ones, the blue, and the green, and exchange them. There's 3 set of 3 rows. So those sets of 3 rows, there are 3 of them. There's 3 factorial ways in which you can reorder them. And you can do the same thing to columns. And there's 3 factorial ways to do that again, because there are 3 sets of 3 columns. Within each of these bands of rows, I can exchange the first row with the second or the third. So the first 1, 2, 3 rows, you can permute them in any way. 4, 5, 6, you can permute them. 7, 8, 9, you can permute them. And the same thing with the columns. First column, second and third, 4th, 5th, and 6th. 7th, 8th, and 9, you can permute those. So that's the 3 factorial to the 3 times 3 factorial to the 3. And then you can do reflections across diagonals. And actually, at this point, I only put that you get about twice as many. So you can think of, well, there's this diagonal, there is this other diagonal. But actually, and there are a few others, there are the rotations. But if you consider all of these together, by doing some of the permuting of the bands and the rows, you will be doing some of the reflections, transpositions, and rotations. Okay, so you only get about twice as much, twice as many when you consider all reflections, transpositions, and rotations if you have already done all of the permuting rows and columns. So in the end, on average, you get about this many new Sudokus out of every one Sudoku board. So if you have a solved Sudoku board, you can get as many as this many new Sudoku boards by applying symmetries. And the good thing is that we can treat them all as the same. If you can solve one, you can solve all the other ones. If you can solve one with 16 clues, you can solve all of the other ones with 16 clues. And if you cannot solve one with 16 clues, you cannot solve all of the other ones with 16 clues. So this is going to considerably reduce how much we have to compute if we actually just treat all of the Sudoku boards that are symmetric as just one. Okay. So we can go from the 6.6 times 10 to the 29 to 5.47 times 10 to the 9 classes, equivalent classes you can think of Sudoku boards that we have to check. Now, there is an approximation here because there are a lot of boards that when you apply the symmetry, you get the same board. So it's not true that for every Sudoku board, you're going to be able to come up with this many new ones. Some you're going to get more than that, some you're going to get less than that. Well, yes, this is sort of like on average how many you're going to get. So some you're going to get more, some you're going to get less. But it shall be about this. So now we have reduced the every possible Sudoku grid part of the problem. Now I want to reduce okay, now that we have this many Sudoku grids, one per each class of symmetric boards, do we actually have to check every single set of 16 clues in one of them and see if I can solve that one uniquely? There are 81 choose 16 ways of choosing 16 clues out of the 81s. So that's tons. Okay, that's a lot. So is there a way for me to reduce that? And the answer again is yes, there is a way. And the way to do it is looking for special places that you actually must absolutely have a clue in. So for instance, let me give you an example. Suppose that I have this Sudoku puzzle in here. It's not a board because it's not completely solved. But imagine that you have this puzzle. I give it to you and I say, can you complete it? There are only 4 cells left. So this will be very, very easy to do. Only 4 cells left. And you start thinking and go and say, well, in this square you have 1, 2, 3, 4. I'm missing a 5. I'm missing a 9. So I'm missing 5 and 9. And in this one, you're also missing 5 and 9. And in this row, you're missing 5 and 9. And in this row, you're also missing 5 and 9. And at this point, you realize that you can solve it like that. 9, 5, 5, 9. But you could have also solved it the other way around. Putting a 5 on top, a 9 here, a 9 here, and a 5 in here. And they're both valid ways to complete this puzzle. And what that tells me is, if I'm going to start with this starting board, and I want to choose 16 clues to check at the beginning to only keep those clues and check if that board has a unique solution, I better choose one of these 4 orange ones. Because if I choose some other 16 clues, and I don't choose any one of these 4 orange ones, then you know that there's more than one way to solve it, because eventually if you come across something like this, there is at least 2 ways to complete it. Okay, so you know that you have to choose one of those 4, and that's super helpful because now instead of just choosing any 16 starting positions, you know that one of them have to come from this set of 4 clues. And for instance, it doesn't have to be a set of 4 in general. This is another example where if you look at these 9 blue entries, if you remove them, there are several ways to complete that puzzle. So if you start with that board and you want to check, can I completely solve that board if I just start with 16 clues, I better have actually 2 clues in these 9 positions. If you have only 1, there's still more than one way to solve, to fill out those 9. So you need at least 2 of them. So 2 out of the 16 have to be in this set. So what we're doing now is, instead of saying, okay, check every single one of the 81 choose 16 possible ways to choose 16 clues, you have to say, no, some of the clues have to go here and here and here. And when you do that, you're reducing how many things you have to check, how many things the computer will have to check. And this set of, like the 4 orange cells in here are called unavoidable sets. In the same way, the 9 blue ones on the right, that's called an unavoidable set. And the name makes sense, you cannot avoid it. If you want a unique solution, you have to put clues in those sets. And a typical Sudoku board has about 360 unavoidable sets. So there are plenty of them. So if we have a good algorithm to find them, then we know that we have to put clues in them. So with those 2 ideas, use symmetries to reduce the number of Sudoku. So things that have the same boards that are in the same equivalence class of symmetries, you treat them as 1. And then the second one is you use unavoidable sets to know where you have to put the clues. With that, we'd reduce the problem enough, or the researchers who did this reduced the problem enough to be able to, on a almost supercomputer, here are the specs, to be able to check every possible Sudoku grid using the symmetries, and every possible 16 clue starting position, well, not every possible, the ones that we actually should have been checking. So we were sort of like efficient in using symmetries and using unavoidable sets to be able to check that indeed, if you put 16 clues, then there's always more than one way to finish, to complete that puzzle. Okay, so now that we have examples, and this is one where you have 17 clues, the one in here. So you have one example, this one has a unique solution, and you cannot push it down to 16. There's no way to have 16 clues and have a unique solution, so 17 is the number that we're looking for. And that's how you can use ideas of symmetries, which are heavily used in abstract algebra, to help solve this problem. I hope you enjoyed it, and in the next video I'm going to talk about a new game, so I hope you join me for that one. Bye!